In conclusion, the only way you can build a building that will withstand a temperate rainforest environment here in Vancouver is to build wood frame with exterior insulation and a rain screen. And that will protect your building, and there's no reason why it shouldn't last for 50 to 100 years when you take those two steps. The second thing is if it's built tight, in other words, you build it draft-free, then we in the HVAC business have a hope and ability to control the indoor environment. If it's built like we built 30, 40, 50 years ago when the wind blows through the outside walls, we cannot provide a comfortable, quiet environment because we're not properly buffered from the outside world. What I'm going to try to cover in 50 minutes is going to impact every one of you in your business. And I appeal to you to understand this stuff because it's really, really important. And the misinformation out on the street in humidity is deplorable. There's just no grasp of it at all. And the only reason that I can think about that is because we're living in a climate that is relatively temperate, temperature-wise and relative humidity-wise, unlike some of the places where it's really dry on the prairies, or where I lived in Texas for 3 years in Houston, Texas, where you sweat just thinking about going outside. So we have been gifted with a climate that is very temperate, and we don't have a severe, what we call a latent load here. So we've been able to wallow along in ignorance, but those days are gone. So I'm hoping when you leave here, you're going to remember a few simple things. By the way, did anyone here hear this presentation exactly 10 years ago? Was anyone here? It was sold as Simple Psychometrics. Because what I'm talking about tonight is relative humidity, which is the same damn thing, it just rebranded it. Have any of you seen the YouTube that was on our website on Simple Psychometrics? It's been there now for 10 years, explaining what I'm going to go, but there's some new stuff that I think might be of interest to you tonight. My outline is extremely simple, and the only things that count are the ones in red. What the hell is humidity? Number 2, what is the ideal? And number 3, what are the factors that affect it? Because in HVAC, we have an effect. We can't have an effect on that. The rest of it is just minor details that we're going to go through. The problem is that there's a million sources of relative humidity or humidity in a building, and one of them is the actual breath. We are living, breathing cornflake burners. We're burning cornflakes, and the direct result is carbon dioxide and moisture. And we're giving off 1 quart per person per day just in breathing. And about 1/3 of our BTUs that we put in the space, which is 300 BTUs per hour, 300 BTUs per minute, per hour? Per hour, thank you. The 300, roughly 1/3 of it is met by evaporation off our skin. So we are, in fact, humidification devices that are actually humidifying this hotel right now. And because the skin losses to the outside are small, the majority of the cooling load right now will be to strip out the moisture that we're adding into this space. Now, related to this is the tightness of buildings. And we've been panicking for 10 years that, you know, the government is saying we should tighten up buildings, and everyone is throwing up their hands and say, what a stupid thing to do, tightening up building will suffocate these people. The point that I'm trying to make, though, is that we've finally got over this idea that tightness is bad. Today, we're finally waking up that tightness of a building is absolutely critical if you want to be able to control the environment. We're in the business of controlling the environment, temperature, humidity, relative humidity, and our comfort. And yet, if the building is leaky as a sieve and the wind blows, we have lost the ability to control the environment. And Mrs. Smith, my fictitious homeowner, is pissed, and she's just as likely to blame you, more likely you, than the builder for building a Swiss cheese house to start with. So we've come to the point right now, we recognize that there's a necessity for human comfort. Forget about energy efficiency and all that crap. Mrs. Smith is paying for comfort, and that can only be achieved if we build a house that truly buffers her from the outside. Well, what I'd like to do then is show you something that I saw in Powell River about 10 years ago that quite blew me away. Here we have a picture of polyethylene in a halfway built house, just framed up and polyed. And you can see all the poly is bulging between the joists. And you can ask yourself, why is this occurring? Well, that house was by the ocean. There was a huge passive gain that day. It was about 60 Fahrenheit inside the building, about 40 Fahrenheit outside. And the buoyancy of the warm air actually caused the bowing of that polyethylene. And in fact, it's very, very noticeable in this single photograph. The thing is, you don't see this in real life because the insulation will weight it down. You can't see the poly for the drywall. But the net result is that any leakage in the plane of that attic floor will have a chance to bypass through all the places. The electricians cut holes, the poly pans on the bath fans, the plates, chimneys, a million places where air can escape, because what happens in a heated house, what happens is that air inside is less dense, it's buoyant, it wants to escape up and leave because that's how air works. It's buoyant, it rises, and the air is going to come in at a lower level and replacing it. It's really, really, really important to understand the simple things. A little while ago, I did a presentation for Fortis, and they were kind enough to provide a little wee graphic that I really quite like. And basically, it just shows, representing these little dots, air inside a building that's 3 floors high. And in an extremely simplistic fashion, this shows what happens in all houses, and the rate in which that air is escaping into the attic is going to be replaced by air coming in through the plates and plug-ins and everywhere else. And this just goes on and on and on. But the net result is that this is something that happens in all houses unless you have a good seal on the plane of the attic floor. What you probably don't know, it's so simple and it's overly simplified, but this happens 24/7, and the rate at which this happens is depending on how high the house is and how cold it is outside. The higher the house, the greater the pressures on that ceiling, and the colder it is outside, the greater the temperature difference. Therefore, the buoyancy is causing air to enter the house low and leave in the attic. In a case like this, what will happen is your thermostat will try to maintain 72 degrees Fahrenheit at this level. Your basement will be cold and the top floor will be overheating. So stratification actually is a direct result of shoddy construction and less so inadequate heating. Now, of course, the unfortunate and unintended consequences of all this is you can end up with a wet attic. And I've been into hundreds of buildings the last 40 years where you look up with a flashlight at the sheathing plywood on the underneath side, specifically on the north exposed side, and you'll see this kind of crap. Because when you live and breathe in a house and that moisture is escaping the warm environment, it goes up into the attic and it's going to condense on the first cold thing it can see, which is that roof sheathing. And typically the north rather than the south, because you occasionally get sunshine on the shingles on the north in the winter, and it'll bake the moisture out of the plywood on the south side and it'll redeposit it on the north side. The simple solution that's being done everywhere right now is increasing the attic ventilation, which is a complete ass-backwards way to do things. Attic ventilation no longer works today when you have R40 in the attic floor, because that insulation is so good, that attic is outdoor temperature, and attic ventilation will not work at all. In fact, it can be shown to be negative effects in some cases, but it did work 20 years ago when the attics were warm. The moment you insulate the attic floor, you've lost all the ability to positively vent this in October, November, December, and January and getting rid of that moisture. Your wood is going to be accumulating that moisture for the entire winter period, and you just hope like hell that you get to April and you haven't reached the mold threshold before the summer suns hit the roof and boil it back out through the ventilation that you have. Now, I'd like to talk about something here about absolute humidity and relative humidity. If any of you leave this room and you ever once talk to me and you confuse the word absolute humidity and relative humidity, I will personally hunt you out and kill you. There's absolutely no excuse for this because they're totally different terms, and I hope, if nothing else, you remember that when you leave here tonight. I'd also like to suggest something else. This is a pan of water, and this pan of water is going to seek its own level. It doesn't matter how I tip it, it's always going to seek its own level. Well, that's common sense, and that's something everyone knows about. The subtle thing, however, is that moisture of the air also seeks its own level. I challenge you, the next time you get out of a shower in a bathroom that's all steamy and everything's stinking dripping wet, before you towel off, open up the door to the rest of the house, and you know immediately you're going to shiver, but I'll bet anything that you're not guessing as the correct cause of your shivering. What happens is the moisture level in that bathroom is going to diffuse almost instantly into every other room of that house, because nature abhors a gradient. We cannot tolerate a moisture gradient. And we're getting into that right now. This moisture can diffuse out of that bathroom almost immediately. The walls, ceiling, and floor will stay soaking wet, and that'll take 10 hours, 12 hours to dry in this climate, but the moisture in the air is going to dissipate immediately, and you're shivering not because the bathroom air got cold, because the relative humidity drops so fast, so far to equal the rest of the house, that you're shivering like mad because you're evaporating a huge amount of water from your skin. So this is getting now to what I want to talk about in relative and absolute humidity. Okay, now, do you have that little box? Curtis is going to pass around some little wee bags of wheat. And I've done this for a reason. In the English scale to which TECA courses are written, we use the inch-pound system, and weight in small quantities is not grams, but grains, GR. In that bag are 78 grains of moisture. 78 grains of moisture is the amount of moisture that you're going to have at any one time in an average house in Vancouver in 10 cubic feet of air. The biggest garbage bags we could buy were 3.5 cubic feet each. So you've got one bag here. Pick up that other one, would you? We have 1 pound of dry air in these 3 bags. And inside those bags is 78 grains, representing the weight of the moisture that's in this absolute. There's no term relative humidity in that bag. It is weight. There's 78, 72?
63.
73. 63. See, I'm all wrong. 63 grains of moisture is the amount of moisture that's going to be in these bags at normal 50% condition. And it's important to remember that this is a weight measurement in a weight of air. So this is 1 pound of dry air, and we're stuffing 63 grains of weight of water in the air, and that is what we would call a normal 50% humidity. So the relative humidity is 50%, meaning it's 50% of what it can hold, but the absolute humidity is measured in weight, in grams. And this is really, really, really important to understanding how heating and cooling and dehumidification, all this stuff works. There's absolute, which is weight, and relative, it's a percentage of what you can hold before your bathroom ends up as a steaming, stinking mess and water drips off the walls. So from that, you can easily see that that is 100% relative humidity, because the moisture in that air is such a high level, it literally has nowhere else to go, so it's actually forming a cloud. So in certain nights today, you can actually see high-rise building, you see the bottom, but the top part will be in a fog. That's because that top part of that just happens to be meteorologically in 100% relative humidity. Absolutely loaded to the gills, to the point where if I was riding a motorcycle in these conditions, I'd get friggin' soaked in less than 5 miles. So in a foggy condition, if you're a street biker, you're going to be wearing a bell staff or whatever you need to stay dry. It's just a fact of life. Okay, so now I'd like to get into this chart over here because it's really, really, really important. When Curtis brought his crew over and I victimized those poor suckers on Thursday and beat them up with the trial run of this so he could have a chance to make some comments, we did this on the floor, but he said that's not going to work very good for you guys. So Curtis did this all tonight here. We've got a little thing here that I want to try to show you how this all works. There's a red line at the bottom, and there's blue lines going up. Blue represents wet, red represents dry. Red is temperature, blue is the absolute moisture in grains of moisture per pound of dry air. So here we're going from climbing on a 777 and flying to London. The outdoor humidity in relative terms is 100%, but because it's so cold, there's squat for moisture in that air. It comes in through the turbines, it's compressed, it's brought into the cabin, And the relative humidity, when it's brought up to 72 degrees Fahrenheit, is absolutely zero. Why do you think they pour as much liquid they can down your throat when you're in flight? Because you're in an environment where your body's releasing enormous amounts of moisture because your evaporation rate goes off through the roof in that environment. Okay, so this chart here says that when it's 40 below, this line here represents the line representing the maximum moisture that air can take at any one condition. At 40 below, you can see that it can hold about 1 grain of moisture per pound of air. In other words, you cannot put any moisture in cold air. It won't hold it. As the air warms up, you can see that we can get more and more and more grains of moisture and more, and it goes right off the end of this chart. Okay, so this is called the saturation line, which means if I was taking a shower at 0 degrees Fahrenheit, which is stupid because it would come out in ice. Let's try 31, 32 degrees. This is the only amount of moisture that would get before it fogs up all the air. The warmer you have your bath and the more moisture you can stuff in the air before it fogs the mirror and totally fogs up the whole room. This is called the saturation line. It's just a magic point where you cannot stuff any more grains of moisture in at that temperature. So as your temperature warms, that air can absorb more and you can stuff more and more and more moisture into that air. This is the 50% point, and I'm going to use this as a reference for the rest of the talk because this is really, really important. And then 30%'s also got some importance that we're going to talk about later. Okay, so here we have what's called the grains of moisture in a pound, and this is temperature. This is something a little bit different. A dew point temperature means that at any one condition that you have in your house, what temperature would the surface have to be before it condenses water? For example, if you drink cold beer that's exactly 32 degrees Fahrenheit, and you're sitting in this condition, would your beer condense? Well, you go over here to the dew point, and if you want to drink beer in an average day in an average house in Vancouver, you cannot drink beer that's colder than 53 degrees Fahrenheit, because 52 degrees Fahrenheit will leave a ring on your coffee table. So this is dew point, and this is really, really important because you can have a back closet in a house with clothes up against the closet, and your gyprock temperatures in that outside wall can go down below that dew point, and guess what happens then? It molds between the clothing and the gyprock. And I've seen it where the clothes, you don't even have to hang them on the hanger anymore, they stick to the gyprock. Okay, so any questions on the fundamentals of this chart? There's been thousands and thousands and thousands of engineering hours go into this since Willis Graham invented this 100 years ago. Nothing changes. It's the basics by which everything in this world works in moisture. Any crazy questions? Anything's fair game on this now, because we will not come back to this. I'm assuming that you know this before we bring in the next level of complication. So again, if any of you guys confuse absolute humidity, which is a measure of grains of moisture per pound of dry air, and the relative amounts, I will kill you, because it's clear now that the relative humidity, that the grains will change depending upon your temperature, because as your temperatures go up, your relative humidity can stay at 50%, and yet my grains can increase. There are two separate parameters here. The grains is an absolute measure because it's not dependent on temperature. The relative is highly dependent upon temperature. Any questions? Okay. This slide is about 10, 15 years old, and it shows where the public and the industry was thinking at the time. In relative terms, we went for humidity in this little chart from 10%, which means you're going to blow away in a desert, right on up to here to the bathroom where that woman is sitting there in a cloud. And up here is temperatures, and I'm just taking a temperature 72 degrees Fahrenheit, 22 C. It's a good place to be. And this was the range that a few years ago was thought to be a good place that we should be shooting for in a building. There was some recognition that if you give about 50%, that you can get into problems, especially in Prince George. Because when you're at a cold climate, your window's cold as hell, and 50% is going to sweat, and you can't see them out, and they're going to ice up. Well, I'm going to show you right now, this is quite dated information, and there's damn good reason right now that the band that we should be shooting for is an awful lot tighter than here, and I'm going to bring you evidence right now to show you that this information is dated and that the target that we should be shooting for is a damn smaller bullseye than we would find acceptable 20 and 30 years ago. Okay, a little bit on instrumentation. The reference by which all this instrumentation is done is what's called a sling hygrometer. And basically what it amounts to is two identical thermometers. This has got a little bulb with, in my case, mercury, because I'm old school, and it records temperature. And we call it dry bulb because this bulb is dry. But what you can't see is right beside it is I got an identical thermometer here that's got a shoelace on it. It's a muslin shoelace by definition. It's wet. And this, by funny name, is called a wet bulb. We have a dry bulb and a wet bulb. They're identical. And if you swing this for exactly 120 seconds, which do you think will get cooler? The wet bulb, right? Because it's shivering, it's evaporating. If I went into that woman's bathroom that was all steamy up right now and swang this, would the two temperatures be different? What would happen is that in 100% relative humidity, this can't shiver anymore because it can't lose any moisture, so the two become the same. So in other words, the drier it is, the more the difference you have between these. And this has got a little built-in slide rule where you can slide it back and forth and it'll tell you exactly what the relative humidity is in this condition. Now you look a little bit like a doorknob doing that. So there's electronic methods of doing that which will read out temperatures and relative humidities that are as good, but they're not as accurate because the reference by which these are created was actually from a wet bulb and a dry bulb method, although this fogged mirrors other methods of testing it. This is always accurate. Electronic methods I've found over our years of business, you find these drifting 5 and 10% quite regularly. Okay, so that's the reference by which this industry is measuring. And these are just some that I buy. Since I've been in business, I love tools and I buy them, but then after I've been around for a while, I use them less and less because you can pretty well finger the problems just by walking in the door. But there's a couple of things that are very, very useful. This is what I showed you, which is electronic. This is the sling. This is a really nice device. We'll get into it later, which is a measurement of wood moisture content. It's a really neat device, and we'll say why it's important later. But it's got two little wee electrodes, and you jam it into wood, and the conductivity between the two electrodes translates directly into wood moisture content. And we're going to show a link between wood moisture content, gapping on your floor, and the relative humidity in the house. The last thing is really quite a lot of fun, and that's this laser thermometer. You'll read the surface temperature of everything, and you can go into back closets and find all sorts of crazy things, and you'll be below dew point in many places in Vancouver housing today. This one here, it's a thermocouple method of temperature measurement. Isn't as useful for what we're about talking about, but it's damn good for POMA in measuring return and supply air temperatures. Any questions on instrumentation? Relatively low cost, relatively simple. Okay, now don't get intimidated. This is the same damn thing as that. In fact, this was created by actually shooting this onto this screen and then tracing it. So this actually is exactly the same as that. But it's got a whole bunch more stuff on it that's important, and I think it's really easy to understand when I show that. This is going from the conditions of the Boeing 777 going to London, where it's dry as hell. This is our temperature in red. This is our blue in absolute moisture. And this is what we call a saturation line, which is the amount of moisture that you can stuff in that air at any one temperature. But what I've done is I put a bunch of diamonds on this to try to illustrate a point. I have blue diamonds, which represents winter design condition, and I have red diamonds, which represent summertime condition. And I'm going to go on to show why Mrs. Smith, if she was concerned by her health, there's good evidence right now that she's seeking 50% RH. And I will defend this in a couple minutes. But I also will defend the fact that there's a certain advantage in keeping the house between 30 and 40% relative humidity, and I will defend that as well. And then you ask the question, who is my master? Well, that becomes a philosophical discussion that I'm not going to touch. Okay, I lived in Houston, Texas for 3 years, and it's rather interesting. Houston isn't a hell of a lot warmer in the middle of winter than Vancouver. But when you look over here, it's one of the wettest places in the entire continent. You can see how much more moisture there is in Houston there is in our desirable set point. Here we want to be, I think it was something like 63 grains of moisture. Up here it's about 128. Like, this is just gross. You sweat like mad just thinking about walking outside. So it's a little bit warmer than our desired point, but it's a hell of a lot higher. So then what we've done is we've taken a look at the 4 cities, Toronto, Kelowna, and Vancouver. And you can see Toronto is a hell of a lot colder, Kelowna a little bit colder than Vancouver, and of course Houston a little bit warmer again. Now, if you ventilate, what you are doing is you're bringing outdoor air in, and you're starting off at a Vancouver condition here, and you're warming up that air, and it's translating this way because you're not adding moisture in ventilation, so you're ending up over here. In the case of Houston, you're ending up at a higher level. In the case, if you're down here in Kelowna or Toronto, you're bringing in air and you're coming in at a very, very low relative humidity because you're taking that air that's 100% saturated, but in warming it, it becomes lower relative humidity. This is the important thing. Like, how do you ventilate a building when it's pissing rain outside, and how do you actually ventilate moisture and get rid of moisture indoors? Is because it's cold outside, and when that air is warming up, it has the ability to hold a hell of a lot more than when it started. Now, I happened to go to an ASHRAE lecture last night that just blew me away. A guy was from Atlanta, Georgia, and he was doing desiccant dehumidification. And he really did his homework before he showed his ass up in Vancouver, and I really respect that. What he did is he took degree hours. So every hour and every degree, he put a pin on this chart. So in other words, what he did is this would represent a degree hour, and you can see there's a lot more degree hours in this band. There's a few out in these other areas, but you can see overall for most of the year that our outdoor temperature conditions are somewhere in this area over here. So on the average day in Vancouver, you're ventilating and you're bringing in less absolute moisture than our target with Mrs. Smith's Health. But the interesting thing is, it's not a hell of a lot less. Because people like to breathe and shower and cook inside a house, you have to ensure that you've got air coming in that's sufficiently low in grains of moisture per pound of dry air that you can add the humidity of normal occupancy and still not exceed this band. I think once you understand psychometrics, you'll find the whole Vancouver issue of putting ERVs in residential properties is going to be completely rethought. And the only reason that this hasn't bitten more people in the ass right now is because we're over-ventilating, compensating for the fact that we're bringing 3/4 of that outgoing moisture back in, which we should not be doing when the bulk of our heating season is so close to the level of absolute humidity that's a target for Mrs. Smith. So that's going to put a bit of a spin, I think, on this marketplace, and the sale of that equipment for not having to put a drain on is a piss poor way to service Mrs. Smith if you really understand psychometrics. So compliments to David Shirk, who did a smash-up presentation for 1 hour yesterday, and it gave me a beautiful slide here to show how this works. Okay, so let's take a look at what are the targets. This slide is 45 years old, and it comes from TransCanada Glass. And it shows you for fun, if we were in a design condition in Vancouver, it may be around here, 23 -5 Fahrenheit Celsius, that a single glazed window can hold about 27%. Well, you can see this is below the target that we would like for Mrs. Smith or Mrs. Smith's building. So we really should be using maybe double glaze where we can handle between 53 and 58%. So one could argue from a point of view of condensation resistance, forgetting about the sash and forgetting about Mrs. Smith being stupid by having really heavy curtains in front of the windows, that a double glazed window will keep us able to support a relatively moderate amount of relative humidity or grains of moisture in that air without causing undue problems. This is center of glass. It does not reflect the frame, the sash, or any of those thermal bridges. If you got the money and you're willing to pay, you can go to higher resistance to moisture by using triple glazing. And you can also see that increasing the glass spacing from 1/4 to 1/2 raises you from 53 to 58% because the air has some insulating value. And right up to 3/4 of an inch, it's a gradually increasing R value. After that, you lose your shirt because it'll start to tumble within the 2 panes. Is glass an insulator? No damn way. What's insulating is the still air between the glazing layers and a still air on the outside of the outside glass and a still air on the inside of the inside glass. The sum total is what gives you R1 for single glass, R2 for double glass, R3 for triple, and then you can start putting films on top of that and getting yourself to R5 and do so reasonably economically today. But R5 is still pretty crappy compared to an R of 20 or 30 in the wall. Okay, so this is really old information, and this was based upon TransCanada Glass trying to defend itself against accusations of a lousy product when people had problems with condensation. Now, there's another possible target you should go, and how many people have been to the Provincial Museum in Victoria? Few of you. In the Provincial Museum, by requirements, you have to have a strip chart recorder, and you'll find that in the floor there will be a device that has a drum that records temperature and relative humidity, because in order to exhibit really fancy world-class exhibits, you have to prove the ability to maintain relative humidity, because relative humidity is a direct factor on the ability of wood, paper, natural artifacts to be stable and preserved. The temperature that you keep your museum at is not important, and you're allowed in a Class AA museum to swing from 66 to 86. They don't care, but you bloody well better maintain the RH, or you are ineligible to exhibit the better exhibits that the world has to offer. So that's one target you should shoot for. Now we're getting into gapping. Hardwood floor. If you're a carpenter, you recognize that wood changes dimension. The wood does not change dimension based on grains of moisture, but wood responds to the relative factor, which is confusing as hell. You'd think with more grains, it would have more absorption. But no, the ability of the wood to absorb is based on the relative humidity. It's not based upon the absolute. So it doesn't matter where you are temperature-wise, it looks at relative. Now, what this means is that wood has a unique quality. It will not change length. The little tubes of the cells, to use your word, I think it's a good one, they don't change length, but the spacing between them does. If you've got expensive flooring, you've got what's called edge grain wood. And this is much more stable than flat grain wood here, but this costs more. But this will expand and contract half as much as this will, but this is 400 times more change of dimension than the length. This is 800 times more sensitive to change in length with a change in the moisture content. So how do we link the wood moisture content, the expansion, and the relative humidity? The hardwood floor guys know this, but I don't think they really know it except the seniors in the company. The guys laying the floor, they don't know squat about this. But it's important because you're going to be the one that's getting the flack from the gapping that happens. Okay, here's another little graph. All wood behaves somewhat similarly. But if I swing from 30% relative humidity to 50%, it shows that the moisture content of the wood is going to go up with rising relative humidity. And you'd think with a 6% moisture content to maybe 8 or 9%, who cares? It doesn't matter. Well, that's why any hardwood floor layers that doesn't have a what do they call it? No. What? Moisture meter? Moisture meter. Isn't that what it's called, Merck? Moisture meter. If they don't have one of these, they aren't doing their business right. You have to have that. So what happens is, on the next slide, it's going to be quite graphic. If I have a moisture content that goes from here to here, I have a shrinkage that goes from here to here. But what does that mean in reality? That lousy little bit of difference in moisture content will put a 1/16 inch gap for every 6 inch wide of board that you've got. And there's a million ways you can play games of that. You can put cheater strips in, or you can put in cross-laminated engineered floor that tries to arrest the dimensional changes by the plywood cross-laminated below it. But the bottom line is wood is a natural ingredient and it works. So there's a certain argument right now that satisfying the needs of the builder needs to control the relative humidity. There's another thing, and this lady absolutely blew away the audience when she came to ASHRAE in Vancouver just before COVID. I went up to her afterwards. I said, damn it, this audience and I needed to hear what you had to say. I want you to come back a year from now and tell us the same damn thing that you told us before, because it'll take us a while to fully register what you had to say. Because in the building community, we're generally concerned with trying to keep the RH down, because we know there are problems when that relative humidity or the grains of moisture get up into levels more than around 63 grains per pound. She had an argument that was completely offhanded, to the point where she was so frustrated with piss poor operating conditions in North USA where she worked, she decided to do something about it. When she took her apprenticeship, she went as a surgeon to East Africa, and she found out the results and post-operative success was higher than she was getting in the best facilities in Boston area. She wanted to find out why, and it took her a lot of years to collect the data, but she was able to show that our body's defense mechanism against bacteria and virus went into the toilet when we get below 35% relative humidity. We need to have 40 to 60. I've met her in Boston, and we sat and yacked for 4 or 5 hours this summer, and she's just a delightful person that is interested in sharing her passion. But she went actually back, quit being a doctor, went back and took architectural degree, and she's a practicing architect and a surgeon, because she wanted to understand a lot more about what it took to build a room to make her profession of surgery work better. Well, here's how it works. Inside the lungs, you have little wee sacs called alveoli sacs, and inside those sacs are little wee air things like this, where air comes in and goes out. It comes in at 21% oxygen, and inside here, the blood from your heart is going around these little wee sacs. Carbon dioxide of our combustion from our cornflakes enters that air, the oxygen is absorbed, and it goes back out. The wet mucus layer inside that lung tissue is extremely sensitive to the relative humidity of the air that you're breathing. If it's dry, its defense mechanism goes into the toilet. And what she learned in her years of research was that our biggest source of infection and problems with disease is coming from our respiratory tract, because we're breathing in tons of air over the period of a week. It's a lot of air. And she showed that our ability to fight off bacteria and viruses followed this blue line. So she's saying between 40 and 60 had minimum risk of disease, but as you get below 35%, these risks went up drastically. That's a whole new twist. That was something that was unaware of to the engineers at ASHRAE here 5 years ago, and it dropped a lot of people right on their ass. So now, what are the variables that affect that balance point of RH in the house? We've got a target for the house, we have a target for your museum, a target for people. Well, let's take a look at the sources. People, as we're beginning to learn, are a massive source of moisture inside a house. In fact, the people contribute more than the people showering contribute some moisture. Plants are significant. Gas cooking a little bit, regular cooking a bit, but you can see that the 4 people are the significant contribution of moisture internally inside that house. Now, forgetting the stupid things, because this slide's 40 years old, crawl space that are uncovered is just idiotic. It's no longer allowed. Damp basements, unfortunately, are far too common, but you can see that the 4 people are actually smaller than the problem of a new house. New house, you're drying out thousands of board feet of dimensional lumber, plus curing concrete. BC Hydro knew 30 years ago the first year heating bill in an electric heated house is going to be much, much higher than after that, because of 2 things. It takes so much energy to dry water out of a frame lumber, and number 2, all those studs penetrating the insulation of the outside wall conduct heat like mad when they're wet, and less so when it's dry. But you can see the people here isn't as significant as the new house situation, so your relative humidity in your first year will always be higher. Firewood's not really an issue. And then we have damp construction. We have a major issue. It's one of my soapboxes for years. We damp-proof the outside of our foundation wall, put the perimeter drain such that the top of it is below the bottom of your concrete layer, but the bottom of the footing and the bottom of the drain are equal, which means that your slab is generally in contact with wet soil, and the footing is worse because that's going to wick water up. And anyone in the building industry today that builds a concrete wall and he frames it on the inside with poly and bats and shiprock. Should be shot because it's a flawed concept, and you're going to totally rot that basement out, and it's going to stink. And I can get you into issues that I was involved with some time ago in defending a heating contractor with mustiness in a theater room. It was incompetency in the building that caused this. It was not an inadequate ventilation. We have a whole write-up on that one. Concrete wicks water like mad. Even ceramic tiles will wick water like mad. It's basically a balance here. And you can see if I move this pointer this way, I'm going to relative the humidity that's lower. And if I push weight over on this side, the relative humidity goes higher. Now what I've asked Curtis to do is I have 17 blocks here that are potential influences on where that balance point might lie in a house at any one time. And he's selected a few here that I'm going to ask. If I have a large house, will I generally have a higher relative humidity or a lower relative humidity than, say, a medium-sized house? In crude terms, would you find two people in a big house or two people in a little house having more humidity, more relative humidity, or lower relative humidity? Of course, because you got 100 plug-ins in the outside wall, a lousy job, and a hell of a lot more lineal perimeter of plate. You have the same humidification force, but you have a whole bunch more escape routes by the Swiss cheese of the average construction today. So we're going to put the word large house on this side here, which has it lowering the relative humidity. The next one he's put is a tall house. Do I have a greater likelihood of dryness or wetness in a tall house than a short house? Drier, because a stack action is more dominant. The taller the house, the greater the pressures that will cause air exchange. Single level slab on grade. Drier or wetter? If any of you guys go to Vancouver Island making sales calls, all the cheap hotels that I stay in, motels, single level, slab on grade, concrete block, they stink with mildew and mold. They're all baseboard heated. You go out of that room, you shut off the heat, close the windows. My protection method would you go into those places, open up the window half an inch, turn the bath fan on, turn the heat to 80 degrees, get the hell out of Dodge for 2 hours, have dinner, go somewhere else and come back, and I can probably make it without pneumonia by the morning.
Wipe your feet on the way out, right?
Teens, which side of the container do I going to put these guys? Wet, yeah? Wet. Too many showers, too many people breathing. Teens, they shower, right? Okay. You were once one, you know? A long time ago. Well, longer for me. High occupancy, well, that's a no-brainer. Now, this one's going to choke you. Forced air heat. Am I going to put this on the right or the left? And you bloody well better defend your answer, I won't buy it. Come on, guys. Get some consensus around this joint, huh? Right or left? Left? Why the hell is forced air heat going to humidify my house? It's not. Why is it going to dry the house? Because until a few years ago, all the furnaces we put in had a 4-inch in the return, right? Every time the fan started, you were ventilating the house, which I believe is the cause by which we think circulation is ventilation, which it ain't, but it was to some degree some years ago.
Sorry. Sorry. Bugging us all.
It's hard to get good people, you know?
Sorry.
Thanks, dude. Again, thank you. You definitely saved some of my credibility. What little remains. So forced air, we're going to dry the house, right? Okay, here's one for you. Insulation. Am I going to dry the house or wet the house with insulation? Now hang on a sec, guys. Insulation to minimize conducted or skin losses is a completely different animal than an air barrier that confines the air within the structure. So whenever you're building, you're thinking, you're talking today, separate thermal conductive to the outside and that of air exchange through piss, poor, leaky construction. They're two separate animals. The sum is additive, but they're independent if you want to understand it. So insulation, what does that do for a house, by and large? Makes it warmer, right? Your surfaces are warmer. When a house is insulated, people are more likely to keep it warm. If a house is lousy insulation, people go broke and they will not tend to keep it warm. So for a given number of grains of moisture per pound, the warmer that I get, the higher that I go in the red bar, my relative humidity will drop. So you buy this if I put it on the drier side. All right. Is that okay, Curtis? All right. Damp climate. Yeah, of course, it has to be. Because we're bringing in air right now that's friggin' wet. It's 100% relative humidity, although it doesn't have a whole lot of grains of moisture in it, it's still coming in pretty wet, as opposed to flying in that airplane when it comes in dry as a firecracker. Okay, so in a damp climate, mild climate, we're dealing with warmer air, milder air. Here's a twist for you, B-vented water tank. What about you gas fitters? Drier, right? You're ventilating the house. Do you know how you increase the ventilation on a hot water tank? Crank up the water temperature. You're sucking more air off the basement floor and sending it up through the chimney and ventilating your house. In fact, it's a great way if you've got a really piss-poor built basement with all sorts of capillarity coming into the basement. It doesn't affect your back closets because the water tank gobbles it up and sends it out before it can cause damage. These are wonderful devices. We should go back to them today. South exposure. Where do you want to put this guy? Dry, right? Dry. Like right now in Vancouver, I'm living in a 1952 shack. It faces south. If you model that house, it costs 30% less to heat than if I rotated it 90 degrees. Passive gain with single glazed windows does cut off your bill even in Vancouver when you don't get any sun. Shit, which side to go on? Left. Last one, electric heat. Now be really, really careful with this. It's a dangerous question I'm sucking you into here. Am I going to put this on the dry side or the wet side? The thing is, see, when you heat with electricity, you're not exchanging the air with outdoors. All you're doing is you're accepting the fact that I'm sitting here and I'm going around in circles, around and around and around. So whether I'm heating with gas and a two-pipe system or a heat pump, electric furnace, or baseboard, this cannot add any moisture to the house because it's incapable of answering moisture to the house. Now, I was in Houston, Texas for 3 years. Is gas dry or wet? We had an apartment, 5 kids, mom and dad, and it had 3 space heaters. One in the can, which I love because it was porcelain. You could sit in the toilet, radiate your needs. It was great. One in the living room, which I like because I could take off the hose, fill balloons with it, and send them up in the sky. The one in the bedroom was a small version of that, and they were great, but they all vented inside, so gas heat in Texas is wet heat. Electricity is called dry heat, but here, because we vent gas appliances, electricity is actually wet heat, and gas is dry heat. So you can't believe half of what you read. Or half of what I say, right? So anyway, what I'm trying to show here is you can be replaced. Okay, so the moral of the story is, see, you in the HVAC business are being told that you have total control over the building, but there's a bunch of wild cards, plus the builder may be building Swiss cheese or not. That's why I'm an advocate of blower door testing houses. You can find out with no prejudice whether the builder is competent or whether he's promising the world and he has absolutely no ability to deliver a house that you can potentially heat and cool because it's out of control with its environment. Now we have to get to the final part of this, and that is the target that we should be shooting for. The ventilation is a big factor here. And one of the things that I think is important, because this is a variable, is that this table was produced, and I'm somewhat responsible for creating this table in the BC Building Code, but I think today as we mature, we're beginning to realize this table overemphasized the amount of air exchange that we should be providing in buildings. And what irks me the most is people are putting 85 CFM exhaust fans on secondary suites in basements, which is just plain stupid. But the thing to remember, even at 15 cubic feet a minute, we're changing the air in that house with almost 1 ton of air in one day. That's a hell of a lot of pounds of air exchange, and we got to remember the power of running systems continuously. People think 50 CFM is small, but they fail to realize that that is 50 per minute times 60 minutes an hour times 24 hours. It adds up quickly. We're going to be diminishing these tables, I can hope, in less than 10 years when we wake up to where the Europeans are. So then we get into this issue, what are our targets? Now, I've got another piece of information in this chart that might be of interest to you. Here I have 11,600 degree days, which means in Houston, Texas right now, I'm heating to the tune of 11,000 degree days, but I'm cooling to the tune of 3,000 degree days. So if I was looking at a ventilation strategy, where would I cater my interest? To serve the cooling or serve the heating? The big one, the cooling one, right? Because I'm going to spend a hell of a lot more power in cooling than I would in heating by a factor of 3 to 1. So if I was looking at a ventilation strategy, the first thing I got to do is I got to figure out how I'm going to knock this humidity down right now, all the way from 128 grains down to 53 or something, which is a massive amount of energy. Now, while we're on this chart, there's something else that's important. If I take air from 0 to 100, in 1 pound, I'm going to absorb 17 BTUs. If I take air from nothing up to 128 grains, I'm going to absorb the same amount of energy. So you can see there's a hell of a lot of latent, what we call moisture energy in that Houston air, and I got to be aware of that. Now, Vancouver, on the other hand, you can see right now, if you don't have internal gain or whole out-of-control passive gain, the amount of moisture in the outdoor air in Vancouver is absolutely nothing. So we don't have to worry about it. Secondly, we have 83 degree days of cooling, and our heating load is 5,000. So our whole concern is to look after ventilation efficiency when we're in the heating season. Our 2 targets then I'm going to support are Mrs. Smith at 50% according to Stephanie Taylor, and I'm going to defend these at the lower percentage because most buildings today are not built what Mark Govin would say with the Vancouver test hut. We should be using exterior insulation in all buildings, then they would support the higher relative humidity before getting into cold corner dew point problems. You can never build a house that's healthy if it's not insulated, and the only way to properly insulate is exterior sheathing on a 2x4 or 2x6 wall. You will never get a healthy, comfortable house with standard stick framing because the 15% of the outside wall is stick frame, and the insulation value of a 2x4 and 2x6 is lousy compared to the bat which you're displacing. Now, the issue always comes up right now, ERV or HRV. They both do exactly the same thing. You're exhausting air from inside. In the case of the HRV, this moisture is going through the core. Some of it condenses and drains, but 3/4 of it goes out as what we call super saturated air. It's loaded to the gills with moisture because it's being cooled in the process of leaving. The ERV is exactly the opposite animal, but I believe it's being misapplied. The air comes from inside, it's going through the core, and it's going to take the relative humidity, the absolute humidity outside, which we know is a little bit lower, and it's going to pick up moisture from the air that you've exhausted, and it's coming back in here, nearly 3/4 as much moisture as what's leaving. I would argue that in Houston, Texas, that's a huge plus. I would argue equally forcefully that it's the wrong approach for this city. So now when we come back the full circle, where is our target now? If you take all the information we've been put together regarding the building and Mrs. Smith, we say to ourselves, this big, huge blue band is way too loose. We don't want to go more than 50% because most buildings won't take it. And the farther you go north, the less you're going to be able to take this humidity before you cause damage and ultimately air quality problems for mold and mildew. But we also know that we shouldn't be going below 40% relative humidity because our lungs react badly and our defense mechanisms go into the toilet. So basically where we're sitting right now, we're trying to maintain our 72 degrees Fahrenheit, and you can see the band that we have to work with, but you can also see the dilemma because there's a whole bunch of variables that you're having to face. There's a variable of occupancy, there's a variable of tightness, and you're there at the very end trying to control it all with the ventilation rate in that building. It puts you at a huge disadvantage, but if you know this stuff, then you can defend the limitations to what you can do. That's it.